Geologic time. This is just an interesting little graphic kind of showing our current concept of geologic Earth history. So if you look at the bottom, the Earth formed 4.6 billion years ago. And this just breaks down the actual geologic time names that we've given for defined periods. So we're going to discuss how these names came about, how they're broken down, and how they're all related. So first we need to get a brief history of geology. So we've started talking about geologic concepts, how minerals are formed, how rocks are made, how the earth is formed and deformed because of these. But we really need to understand geology as a science and how it has been developed, because that really influences our current understanding. So we're going to start with catastrophism. This was an early geologic concept, and this was the concept that Earth was formed and shaped by catastrophic events of short-term nature. This was coined and really championed by James Ussher in the mid-1600s, who concluded that Earth was created in 4004 BC and is therefore only 6,000 years old. So he was really the champion of the young Earth theory. Let's go back. So the young Earth theory is that the Earth was formed about 6,000 years ago, and that many of the formations, the Grand Canyon, some very large gorges, mountain ranges, were all created by single large-scale events such as a global flood. That these large catastrophic events are what create the changes on Earth, that there is no continuous ongoing process. Every change that is made by one of these single short-term events. James Hutton is considered the father of modern geology. So he was an 18th century Scottish geologist. He was a doctor and a farmer. He actually published his ideas in Theory of the Earth. He first came to realize and publish on the immense age of the Earth contrary to widely held beliefs of his day, and formulated the principle of uniformitarianism. This states that processes that are occurring today have been happening all throughout the Earth's history, and so that by studying and understanding what is currently happening, we can actually understand what has happened in Earth's past. So the phrase, the present is key to the past. So just compare and contrast. Catastrophism believes that the landscapes were formed by rapid process and great catastrophes, and this is used to fit the rate of Earth's process to the prevailing or biblical ideas of Earth's age, and that therefore if Earth's landscape only changes suddenly, then the Earth must be very young, because there are not many of these sudden large-scale changes. Whereas uniformitarianism states that all the current physical, chemical, and biological laws that we understand today and that have operated in the past, and that to understand ancient rocks, we must also understand present-day process. And this gave way to the idea that geologic processes occur over very long periods of time. If we look today, there's nothing that, let me take that back. There are many processes that happen suddenly, landslides, smaller scale catastrophic events, but there are other processes that occur over very long periods of time, rates of weathering, rates of deposition, and this is really the basis for uniformitarianism. So the first question are, name several catastrophes and the Earth's processes responsible for them. So we've got volcanoes, and the process responsible for them are plate tectonics or mantle hotspots. We also have tsunamis, also caused by plate tectonics. Earthquakes, also caused by plate tectonics. Floods are long-term hydrologic cycle events interacting with topography developed by weathering and erosion. So this is really that relationship between the hydrologic cycle and your current landscape. And these floods can then change the landscape, affecting how that hydrologic cycle continues to interact with that region throughout history. When we talk about geologic timescales and geologic time periods, there are two different ways we go about breaking these down. We use relative dating and absolute dating. Relative dating is when rocks are placed in their proper sequence or order. Only the chronological order of events is determined, not their actual numerical age. So this is where we know that X happened before Y happened before Z, but I can't tell you when that happened. Whereas absolute dating is where rocks are given numerical ages representing important events. So I can say X happened 4 years ago, Y happened 2 years ago, Z happened 6 months ago. That's where absolute dating would come into play. Relative age dating was really brought about by Nicholas Steno. He published Perdomus in 1669, and this was after studying the geology of a Tuscany region of Italy. He reasoned that the sediments which made up the rocks were deposited from fluids, and he summarized his observations into what are now known as Steno's laws: the law of superposition, the law of original horizontality, the law of cross-cutting relationships, and the law of lateral continuity. These are really the basic laws of geology. You have to understand these to really understand how we interpret geologic sections and rock beds and formations. This is really the basis of our current concept of what has happened. So, Steno's law of stratigraphy. The first is the law of superposition. This is where younger layers of rock sit atop older rocks. Okay, because when we deposit, you always have material depositing on top of each other, so it's always going to be younger on top than stuff on the bottom. Law of original horizontality. This is the idea that layers of sediment rock are originally deposited flat. So if you had a slope, and you poured a bunch of sand on the slope, it would all slide down and start depositing horizontally at the bottom, right? Because of gravity and the way it impacts that sediment. So the idea is that everything is always deposited horizontally. So if you have rock beds that are tilted or angled or folded, they weren't always like that. Some force acted on them to move them from horizontal to tilted. 3 is the law of cross-cutting relationships. This is the idea where rock layers A and B have to be older than a rock layer C that disturbs them. Okay, C can't cut through A unless A was already there. Otherwise, you'd have a border of C between A and B where C just broke through B, deposited on top, okay? So for C to actually intrude into A had to be there first. And finally, the law of lateral continuity. This is where the layers of rocks are continuous until they encounter other solid bodies that block deposition, or until they are acted upon by agents that appeared after deposition took place. So weathering impacts, human impacts where we've actually removed those rock units. So this is taking a look at an area of the Grand Canyon. And this just shows the superposition in the Grand Canyon. So if you look, you have the Supai group at the base, which are alternating layers of sandstone, siltstone, and shale. And then you end up with this very large area. It looks like a slope here. This is the Hermit Shale. They're red. They're slope forming because they weather easily. Very thinly bedded shales and siltstones. Then you have these very straight, rigid sides of very weathering resistant rocks. These are the Coconino sandstones. They're cliff forming and they are cross-bedded. And we will discuss cross-bedding a bit in a little bit. And then we have the Toro Wheat Formation, which are shallow marine beds, and they're thin to medium sandy limestones. And then the Kaibab limestone, which are shallow marine limestones, and these are really what rim the canyon along the top. So this just shows we have our oldest rock at the base and our youngest rock at the top. You see how everything is very horizontally bedded? Okay, we have a really good layout of a picture of superposition of your law of original horizontality. So see, everything is very horizontal there. It's very clear and easy to discern. So here we have, the original horizontality. Everything is bedded in those flat horizontal layers. And these layers, they're folded, they're tilted, they've undergone a lot of deformation. So this is because of some sort of pressure that was introduced that disrupted the horizontal bedding of those rock units. Okay, the principle of cross-cutting relationships. Geologic features that cut across rocks have to form after the rocks they cut through, right? You can't cut through something that doesn't exist. Therefore, younger features cut through older features. Good examples are faults or igneous intrusions called dikes. So we talked about faults in a previous chapter, and this just shows how originally these two white layers were a single unit, and a fault broke through at some time to offset them. And the fault runs all the way through. It looks like this gray layer here, and dies out somewhere right around here off the picture. And here we have an igneous intrusion or a dike, and it's cutting through these rock units. These are all rock units that existed before that intrusion. So we have a focus question. No place on Earth has a complete record of rocks deposited since the Earth was formed. Why is that? Okay, this is because of erosion, right? So once a rock is deposited, unless it is buried deep, such as an igneous pluton within the Earth's crust, it is basically immediately undergoing some sort of weathering. You know, it's exposed to air, it's exposed to water, biological factors, and these are all going to start having an impact on the rock and how long it remains in place. Some rocks are more weathering resistant, so they will remain in place longer, others are not. But because of this, there are erosion forces that are constantly acting on these rock layers. So rock layers that are deposited without significant erosional interruption are called conformable layers. This is where we can see a nice continuation of the different rock layers throughout time. There is very little erosional impact through weathering or biological features. These are not very common though. Most rock layers show signs of interrupted deposition. These are called unconformable layers. And the overall grouping of this, of surfaces with interruption, are called unconformities. Unconformities are a break in the rock record or missing time. They are either caused by erosion or pre-existing sediment, or they're generally caused by erosion of pre-existing sediment. Sorry, that sentence is wonky on my slide. Generally, uplift causes deposition to stop, okay, because you have your elevation increasing, so you don't have material being deposited there anymore. It's going to deposit to a lower region. And subsidence causes deposition to resume because you're reducing the elevation, and so you've got a low-lying area. Gravity is going to pull material down towards this direction. When we talk about unconformities, there are three different types. You have your angular unconformity, a disconformity, and a nonconformity. An angular unconformity consists of tilted or folded sedimentary rocks overlain by more flat-laying strata. This is deformation. Deformation occurred during a time that deposition also stopped. So here we have our deposition, our horizontal beds. At some point, deposition ceases, so we've got this uplift, this folding, and then we have erosion occurring because we have now increased the elevation of these materials, increased the rate of weathering, erode off, and then at some point in time, they have eroded down to a lower elevation, and deposition has again resumed. So we have, if you look here, this boundary, this angular unconformity, where we had that significant time period of erosion with no deposition before the whole region was then flooded again and began your deposition again. So here we have an angular unconformity. We have nearly vertical sandstones here, and then at some point they were then submerged again, and we start to get a deposition of horizontal beds of conglomerate and sandstone. And then they have, since that angular unconformity and deposition, they have again undergone a bit of deformation, because you can see these beds are no longer horizontal either. They're slightly tilted. A disconformity is a break in the strata representing a time when erosion occurred. This is more difficult to identify because younger and older layers are roughly parallel. Typically, you have evidence of erosion, such as a buried stream channel. So angular unconformity is typically categorized because the driving deformation process, the uplift, is what encourages that erosion and that boundary of lost time. Disconformities are typically still horizontal beds that have a lost time, typically due to stream channels. You don't have that uplift giving you that change in angle of those depositional beds that really make it obvious that there was something that happened there that is no longer stored in the rock record. Finally, a nonconformity are young sedimentary rocks on top of older metamorphic or intrusive igneous rocks. These imply a period of uplift of deeply buried rocks. So if we get these extremely old igneous and metamorphic rocks with very young sedimentary deposited on top, there was something that occurred to uplift these igneous rocks to the surface and had them erode away and then undergo deposition on top of them. So here we're going to look at an example of a geologic section within the Grand Canyon. The red lines represent unconformities. Identify the different types of unconformities present in this cross-section from the Grand Canyon. Oops. So if you're looking at these, we've got a non-conformity here because we have sedimentary overlying an igneous, a granite, and our non-conformity over a metamorphic here. We have an angular unconformity because we have our tilted sedimentary beds with our horizontally deposited sedimentary beds. We have a disconformity because you see these beds are parallel, but you have this extremely broken depositional boundary between the two. Another disconformity here. And then we have a very defined sequence of bedding from here on up above these disconformities. So we use these relative age dating to work out geologic history of regions. So this is just looking at a hypothetical region. So here we've got our initially horizontally deposited sedimentary beds, A through E, that are deposited in order based on the law of superposition. Uplift occurs or change in the environment, the ocean recedes. So our bed E is now exposed. And we have the intrusion of sill D, which is younger than beds C and E because of the inclusion of, in the sill, of fragments from C and E. Okay, so we have inclusions from the beds below and above it within D, showing that there is intrusion of a layer here. Next, we have an intrusion of the igneous dike F. It cuts through all of the layers here, so we know F is younger than D. And then the entire region undergoes deformation where it tilts the beds. And we know this happens after F. You know, F is already present, which means that the deposition must have occurred, the intrusion of D must have occurred, cross-cutting of F, and then the tilting of the beds. And then finally, beds G, H, I, J, and K are deposited in this order on top of the erosional surface, giving us our angular unconformity. And then finally, the irregular surface and stream valley indicate that another gap in the rock record is currently being created by erosion. So in our depositional bed K, you see it's fairly well intact except where the stream is coming through and eroding that material away. So this is just a brief look at how geologists would use relative age dating to get a picture of the history of a region. So I want you to take a look at this image here and try and figure out the age date of the geologic layers and features. I'm going to give you a minute to take a look at this and kind of understand it before I move on to the next slide. Okay, so if we start from the oldest to the youngest, layer D was deposited first. Okay, because you can see that's the deepest unit. C, we can understand, is an igneous material or a basement because of the dike that later cuts through additional layers. So D is the first that's deposited, followed by H because it is directly on top of D. And then layer A is deposited. Next we have layers A, H, and D undergoing folding. After they undergo their folding, then we have the intrusion of layer C and that igneous dike. And the reason we know that they were folded before the intrusion of C and before the dike is because this actually cuts through the fold. If they had been deposited and this moved through them and then they were folded, you would have seen manipulation in that dike of C. It wouldn't have been such a straight shot. And then fault G cuts through the previous layers. An angular unconformity separates layers A and F, okay, because this is where that fault line ends. And layer F is deposited, followed by layer I, followed by layer B. And then we have a tilting of those layers, giving us another angular unconformity before layer E is deposited. And finally, we have uplift and erosion of layer E, as you can see on the surface here. Now, just understanding the way geologic beds are deposited isn't the only way we do relative age dating. We can also use fossils. Fossils are traces or remains of prehistoric life that is now preserved in the rock and are generally found in sediment or sedimentary rock. Oh, sorry. Oh. Now, paleontology is the study of fossils, but a lot of the information that paleontologists have uncovered is used in the field of geology. Fossils can be preserved in many ways. Some remains are not altered at all under certain conditions, such as teeth, bone, or shells. Flesh and skin are not commonly preserved, except for mummification or freezing conditions. So we have a few fossil types. We have permineralization. This is where mineral-rich groundwater permeates the tissues. The petrified wood or the petrified forest in Arizona is a good example of this. The wood is permineralized with silica. Basically, the mineral-rich groundwater is soaked into the wood, and the silica replaces many of the other atoms within that piece of wood, preserving it. We have molds, which are formed when a structure buried in sediment was dissolved by groundwater, and only the outside shape and surface is preserved. If hollow spaces are then filled with mineral matter, a cast is formed. So here we have an example of a mold, the void space where a trilobite had occurred. And then here we actually have a cast. And this is where that mineral water then seeped into that void left by the disintegrating trilobite and filled in that space as a permanent example of the trilobite. And then we have carbonization and impressions. This is where remains are encased in sediment and the pressure squeezes out all liquid and gas until only a thin residue of carbon remains. This effectively preserves leaves and very delicate animals. These impressions can actually show extremely close details. For here we have a fossilized bee that's preserved as a thin carbon film. And impressions of fish are extremely common this way. There's also amber. This is the hardened resin of ancient trees, which seals organisms from the atmosphere and water. And this can preserve more delicate organisms such as insects. We also have trace fossils, such as tracks or burrows through a sedimentary, through a rock unit that was left by an organism. Coprolite, which is basically fossilized dung, and gastroliths. Only a small fraction of organisms are actually preserved as fossils. There are a few things that need to happen. You need to have rapid burial, and hard parts favor preservation. Soft parts are typically eaten or decomposed. Under the rapid burial, the sediment protects organisms from destruction. The shells, bones, and teeth are much more common in the fossil record because of their hard parts. And those are typically preserved very well in low-energy environments. Creatures with soft tissues are only preserved under very specialized conditions. For example, the Burgess shell fauna are preserved through, it's basically a historic swamp area that really compacted these plants as they decompose, or as they were quickly buried, and preserved the structure in the rock record. So how do we know which rocks were deposited at the same time from area to area? We do this through correlation. So correlation is the matching up of rocks of similar age in different regions. This reveals a more comprehensive picture of the rock record. Correlation is typically done on a small scale by walking along outcrops in limited areas, and rock layers made of distinctive material can be identified in other places. Here's just an example of how we would do correlation by fossils. So say I'm along a highway section and I have an outcrop here, and then there's a bit of gap and an outcrop here, and then if you look on the other side of the road, there's an outcrop here. So we can take cross sections of each of these, draw up a sketch of the rock units, and determine where these rock units match up. So if you look at the example on the left, we have this gray brick-like pattern, typically represents a limestone. We have it present in first and second outcrop drawings, but not the third, showing that somewhere we have an unconformity where this bed was either pinched out or it was eroded. So these correlations give us a better idea, because if we were just looking at this outcrop, we would not even know that this sedimentary bed existed. So it gives us a much more comprehensive idea of the geologic history of a region. This is actually used in a very large scale across many regions and continents. We're actually able to correlate beds from the Grand Canyon through Zion National Park and Bryce Canyon National Park. This is just a very large scale geologic cross-section of an entire region, showing how certain beds are pinched out or eroded away, such as the Grand Canyon area. And those beds are still in existence in very thin sections in Zion National Park, and that there was additional deposition in the Bryce Canyon National Park of rock units that are not present in the other two. But based on this, we're able to see that the Grand Canyon National Park are, the rocks exposed here are younger than those in Zion or Bryce, because the youngest bed in the Grand Canyon National Park right here is actually only about 2/3 of the way through that rock unit in Zion National Park, and only about halfway up through Bryce Canyon, allowing us to really get a complete idea of the depositional environment here. So, correlating with fossils. This idea was brought about by William Smith in the late 1700s and early 1800s. He noted that rock formations in canals in England contained fossils, unlike the fossils in the beds above and below. Rocks with the same fossils were deposited during the same geologic time interval, and distinctive fossils can be used to identify and correlate widely separated sedimentary strata. So when we use fossils, we need to understand the principle of fossil succession. Fossil organisms succeed one another in a definite and determinable order. Therefore, any time period can be recognized by its fossil content. Fossils actually document the evolution of life through time, which is why we're able to use these as a really good correlative tool. So this is just showing his biostratigraphy that he drew up of the difference in the fossils and the layers. When we correlate with fossils, we can't just use any fossils. The ones that we use are called index fossils. They have to be geographically widespread and limited to a short span of geologic time. Okay, if we had a fossil that existed through 80% of geologic history and existed all over Earth, well, it doesn't give us a good idea, because it could have been, at any point in that 80% time span. If we can't use index fossils, we use fossil assemblages, or an analysis of all the fossils present in a rock unit. So fossils are useful environmental indicators. So here is an example of using fossils for identifying rock units. So if we wanted to use an index fossil for identifying rock units A and B, what would we use? So here is an actual drawing of the cross-section. And here's just giving you an age range of the fossil groups that are found. So if you look in rock unit B, we have a trilobite, which existed first 40% of the time in our scale. We have this type of shell, which existed for about 90% of geologic time. Our fern assemblage, which is about the younger 60%. Our starfish, and this other shell, which existed for 90 to 100%. So if we're really trying to get an age of rock B, We're probably not going to use these two guys. They could have occurred at any point in time. We might look at the fern. And again, this shell existed through a lot of time. So what we want to look at are ones that only existed through this blue span, right? So we have a trilobite that existed up to the end of the age of rock B, and a fern which didn't start until rock B. So this has a nice overlap of the beginning and the end of the fossil here, giving us a really good age boundary. When we look at rock A, we have the starfish again, we have this shell again, we have the fern again. We also have a dinosaur fossil and a maple leaf fossil. So here, the best index fossils would be the dinosaur and the maple leaf because, again, they both either begin or end within rock unit A, really giving us a nice bookend for depositional environment of rock A. Here we're looking at 3 different rock beds and here we're looking at 3 different fossils. So fossil A, the trilobite, B is one type of shell, and C is another type of shell. So if we look at the blue bed and the purple bed, this bed contains fossils A and C. And then if we look at the purple bed and the red bed, this contains fossils A and B. So this purple bed here is the only rock unit that contains fossils A, B, and C, giving a really narrow look of when that depositional event occurred. So this boundary here, where it contains all 3, gives us a really good ending point for the first unit and a really good starting point for the third unit. You see how that breaks that down? So the disappearance or the appearance of different fossils can really give us a good relative time period for a rock unit. So here's just another look at correlating using fossils. So these are 2 theoretical outcrops miles away. Oh, sorry. And you can see that the first rock unit here has this butterfly-shaped shell in it. And if you look over to the rock unit on the right, the first bed here has a trilobite in it. Well, these don't correlate. They don't have the same fossil in them. Bed 2 doesn't correlate with that over here. But bed 3 has that same fossil. So it existed and was deposited during a similar or the same time period. You can see they're not exactly the same type of rock based on the patterning behind it, but they were deposited at the same time. And then we have the spiral shell. And then here we have a rock with a fossil in it. And over here we don't have that fossil that exists. But then we do have the same fossil again. So this shows a pinch out or an erosion of a rock unit based on the correlation of fossils that existed on either side of it in both outcrops. Okay, now we need to explore absolute age dating. Absolute dating is done a variety of ways. So here we're just going to review the basic atomic structure and how we go about absolute age dating with radioactivity. So each atom is made up of protons, neutrons, and electrons. And if you remember from the introduction, protons have a positive charge, electrons negative, and neutrons are neutral. Elements are identified by their atomic number. The number of protons in the nucleus is where we get the atomic number. Hydrogen has 1 proton in its nucleus, so it has an atomic number of 1. Oxygen has 8 protons in its nucleus, so it has an atomic number of 8. 99.9% of an atomic's mass is in the nucleus. Okay. The number of protons and the number of neutrons in an atom give you the atomic mass. Neutrons can vary in number in an element, but protons never do. An isotope is an atom with a different number of neutrons in the nucleus. An element can have a different atomic mass, but never a different atomic number. Okay, like we said, the atomic number is the number of protons in an atom's nucleus. This is always the same. Now, the atomic mass can vary based on the number of based on the number of neutrons that are present in an atom's nucleus. Some isotopes have unstable nuclei with bonds that are not strong enough to hold the protons and the neutrons together. These will break apart and decay in a process called radioactivity. There are 3 common types of radioactive decay. We have the alpha particle, which is 2 protons and 2 neutrons are removed from the nucleus, and the mass is reduced by 4, and the atomic number is decreased by 2. You have your beta particle, which is where you release an electron from the neutron. A neutron is actually a proton and electron combined, so if you remove an electron from a neutron, you then get a proton. So your mass remains the same, but your atomic number increases by 1, because you've taken something that was neutral and made it positive. And then electron capture. This is where the nucleus captures an electron and combines it with a proton to form a neutron. Here your mass number remains the same, but the atomic number decreases by 1. So beta particle, you have your atomic number increased by 1. Electron capture, you have it decreased by 1. Some common ones are the uranium-238 isotope. This is an unstable radioactive isotope. It decays into the stable daughter product, lead-206. And here we're looking at a chart of how that parent isotope decays into the daughter product. When we talk about radioactivity and the process where it decays from the parent to the daughter, we talk about half-lives. This is the time required for 1/2 of the radioactive nuclei in a parent sample to decay to a daughter product. Okay, so what happens is, if we say we have 20 of the uranium-238, how long would it take for us to have 10 uranium-238 and 10 of the lead? Okay, we can use the principles of radioactive decay for absolute age dating of rocks. This is a reliable method of calculating ages of rocks because the rate of decay for many isotopes doesn't vary. Okay, isotopes have very defined specific half-lives. The rate of these decays have been precisely measured, and daughter products have been accumulating at a known rate since rocks were formed. So the principle of radiometric dating is that the time required for half of the nuclei in a sample to decay is its half-life. 1 half-life has transpired when quantities of parent and daughter are equal in ratio. If the half-life of an isotope is known and the parent-daughter ratio can be measured, then age can be calculated. So here, say we started with a parent atom of that uranium, and it's 100% uranium, 0% lead. And then as time elapses, we get to a point where we have 50% uranium and 50% lead. This is 1 half-life. And then if you continue on, you get to a point where you have 25% uranium and 75% lead. This is a second half-life because you've gone from 50 to 25. And then as you go on, you go from 25 to 12.5. We're round up here to 13 atoms. This would be your third half-life. And you continue on half of that, your fourth. So this is just a really easy way to determine how time has passed, because if we know how long this time span is to get from 100 to 50, we know how long that half-life actually is in the number of years, we can accurately age a rock unit. So we're assuming here that the half-life of this isotope was 1 million years. This means that this took 1 million years to occur. This took 2 million, all the way to 4 million years here. So it would take 4 million years to get to the point where you have 94 atoms of lead and 6 atoms of uranium. Half-life as a rate measure. So half-life of radioactive parent elements, or half of the radioactive parent elements remain after 1 half-life. 1/4 remain after the second half-life. So the change is exponential. If you look at the chart, it is that exponential curve. There are 5 isotopes that are very important when we're talking about geology and using these for absolute age dating. Are rubidium-87, uranium-238, uranium-235, thorium-232, and potassium-40. This is because they give us they're present in fairly high quantities and give us very stable daughter products. So uranium-238 gives us lead-206, and the current accepted half-life value of these are 4.5 billion years. So it takes 4.5 billion years for us to get to a 1-to-1 ratio. Uranium-235 to lead-207 is 713 million years. Thorium-232 to lead-208 is understood to be 14.1 billion years per half-life. Rubidium-87 to strontium-87 is 47 billion years, and potassium-40 to argon-40 is 1.3 billion years. Another way to do absolute age dating is with radiocarbon dating. This uses the carbon-14 isotope to date very recent events, and this is carbon-14 to nitrogen-14. The half-life of carbon-14 is only 5,730 years. This method is useful for dating events about as far back as 75,000 years or 13 half-lives. This method is most useful for dating remains of organisms, since the content of carbon-14 remains stable in the organism while it is alive. It does not start undergoing that decay until the organism is dead. However, it's only useful for dating events from historic past and very recent geologic history because of that short half-life. And carbon-14 is present in small amounts in all organisms. So it's a really common method, and it's a really good method to use for recent history. But in terms of geologic timescales, it really only has a very narrow window where it's applicable. Rocks can only be radiometrically dated if all minerals formed at the same time. So this is important to know. So this works for igneous rocks, volcanic ash layers, dikes, sills, other plutons, or intrusive igneous rocks. And it can work to determine the time of metamorphism for metamorphic rocks. So it won't tell us the age of that original rock, but it will tell us when that metamorphism occurred, because remember, it reworks the minerals within the rock. But it cannot work for sedimentary rocks, because sedimentary rocks, by definition, are pieces of sediment eroded off of a variety of rocks that are all deposited in one region and then undergo lithification. So a conglomerate cannot be radiometrically dated because it contains rock fragments from pre-existing rocks of many ages. So why is relative dating still important? Well, because radiometric dating is mainly used for magmatic rocks. We can't use it for sedimentary. Sedimentary rocks are only rarely able to be dated by these methods. And metamorphic rocks are affected by several deformational and metamorphic events. So metamorphic rocks will only give us that most recent event. It won't give us a history of earlier events that may have occurred. So if we look here, we have a variety of rock units. We have volcanic ash that can be radiometrically dated, but then we have a sandstone, which is sedimentary, shale, which is sedimentary. Neither of these can be radiometrically dated, but we can get an absolute date of this igneous dike. So we get relative ages here that we're able to kind of pinpoint to a narrow window based on radiometric dates here. So we know that the Dakota is older than the shale, but we know that the shale has to be older than 66 million years because that's when this occurred, but it's younger than 160 million years because that's when our volcanic ash is. So that at least gives us about a 100 million year window when these beds were deposited, which doesn't sound like a really narrow window, but when we're talking about geology, actually gives us a pretty good idea. So the geologic time scale, I've mentioned that a few times now. So 4.6 billion years of geologic history is divided into units of variable magnitude. The time scale was developed in the 19th century, but it's constantly undergoing improvements and being reworked. This is based on relative dating, and absolute dates are added based on the timing of igneous activities. When we break it down, we have eons, which represent the greatest span of time. The Phanerozoic eon began 542 million years ago. Eons are then further divided into eras. So the Phanerozoic is divided into the Paleozoic, Mesozoic, and Cenozoic. Eras are further divided into periods, which are then further broken down into epochs. And we're going to look at a graph of this. Okay, here we go. So we have our eons, we have our Precambrian, and then our Phanerozoic. So geologists look primarily at the Phanerozoic. Precambrian are typically very hard to study. There's not a whole lot of examples of these. So when we look at the Phanerozoic, it is broken down into eras, the Paleozoic, the Mesozoic, and the Cenozoic. So let's look at the Paleozoic real quick. So the Paleozoic is broken down into further periods. Okay, we have the Cambrian period, the Ordovician, Silurian, Devonian. Then we have the Carboniferous and the Permian. Now it's important to note then that the Paleozoic and the Mesozoic are broken down to periods, and that's where that stops. That's as specific as we can get within those. However, once we move to the Cenozoic, we are broken down into periods, and we're able to then further break these down into epochs because of index fossils and because of radioactive and absolute dating. So epochs only exist within the Cenozoic era or within the past 66 million years. The oil and natural gas productive rocks in the Jamestown area and most of Pennsylvania, these were all deposited in the Ordovician to Devonian time period. So the Marcellus Shale is a Devonian shale deposit. The Utica Shale is an Ordovician shale deposit. Okay, so that Marcellus Shale actually overlies the Utica Shale by like 88 million years. So what is the eon that spans the greatest amount of time in Earth's history? So if we're looking, the Precambrian actually spans the greatest amount of time. It's just one we have the least amount of data for. The most detailed geologic timescale begins about 542 million years ago. 4 billion years before the Cambrian is known as the Precambrian, which is divided into the Archean and Proterozoic eons. Those are further divided into 4 eras and represent 88% of geologic time. There are also some unofficial terms associated with the timescale. The Precambrian is just what we call everything before Cambrian. So here's our Cambrian period. Everything before that is Precambrian. It's just easier to put it that way because there's very little information to really divide these up. You almost never hear anyone talking about a specific. And then Hadean, which is the earliest eon of Earth's history. This is before the oldest known rocks. The basic structure of the timescale uses geochronologic time units. So we discussed this already, the eons to eras, eras to periods, periods to epochs. And this is just a weird little comic about geologists dating rocks. Get it? Dates. Okay. So that's the end of that slideshow. Make sure you do your chapter 8 homework. Make sure you do your weekly discussion posts. Comment on everyone else's. And take a look at the syllabus because we are coming up on your research project assignment. So I really want you to start thinking about that and preparing for it. And as before, don't hesitate to contact me if you have any questions.